Hello GATE aspirants. Welcome to part 13 of GATE Thermal and Statistical Physics series. Question number 17. Which of the following relationship between the internal energy U and Helmholtz energy free energy F is true? Now we know Helmholtz energy F is equal to U minus Ts. So U is equal to F plus Ts. From here I can write dF is equal to du minus Tds minus sdt. But du minus Tds, that is minus of dq, and minus of dq is minus of dw, and that is minus of pdv. This will be pdv minus sdt. So from here dou f by dou t at constant v is equal to minus of s. So from here u is equal to f, and we have this equation. So from here I can write s is equal to this thing. So this will be minus of t into dou f by dou t at constant v. So this is u. Now we don't have this in the option, but we have this dou of f by t. So let us consider that. So dou by dou t of f by t, this is equal to denominator into derivative of numerator minus numerator into derivative of denominator, which is 1 upon denominator square. So this whole thing into 1 by t square, and we have this here. So from here we can write u is equal to this is minus of this, so minus of 1 by t square into we have dou by dou t of f by t. So from here we can see that option A is matching. This is minus of t square dou by dt of f by t at constant v. Next question. Consider a non-interacting gas of spin 1 particles, which each with magnetic moment mu placed in a weak magnetic field B such that mu b by kbt is much smaller than 1. The average magnetic moment of the particle is. Here it is given that spin is 1. So the possible states are minus 1, 0 and 1. And we know energy is equal to minus of m mu b minus of m mu b. So the possible energies are, if it is minus 1, then this will be plus mu b. So we have mu b, then 0 and minus of mu b. So from here we can calculate partition function. Now partition function is equal to summation over I e raised to minus beta ei. So that is e raised to minus beta mu b plus 1 plus e raised to minus it will be plus. So plus beta mu b. Now here it is given that this mu b by kt is much smaller than 1. So that is mu b into beta is much smaller than 1. So here we can use this e raised to mu b by kt is nearly equal to 1 plus mu b by kt. So we will use this expansion. So z is equal to, here I can write 1 minus mu b by kt plus 1 plus mu b by kt. So this will cancel out. So z is equal to 3. Now probability of getting that energy is equal to e raised to minus beta ei upon z. So that is simply upon 3. Now average magnetic moment is equal to summation over these values of m can be minus 1, 0 or 1, m into mu into its probability. So this will be equal to, first let us consider minus 1. So minus 1 into mu into we have e raised to, if it is minus 1 then energy will be mu b. So this will be mu b by kt, and there we have minus sign, so this will be minus mu b by kt by 3 plus we have 0 plus 1 into mu e raised to mu b by kt upon 3. So this is equal to, this mu we can take common, and we have this e raised to term. So this can be written as, we have here minus sign also, minus 1 into, and again we will use this approximation. So that is 1 minus mu b by kt, 1 minus mu b by kt, and plus we have 1 plus mu b by kt, and this whole thing upon 3. So mu is equal to mu by 3 into this minus 1 plus 1 will cancel out, and this will be 2 times. So 2 times mu b upon kt. So in the question it is asked the magnetic average magnetic moment is. This is 2 mu by 3 mu b by kt. So option A is correct. Next question. Water at 300 Kelvin can be brought to 320 Kelvin using one of the following processes. Process 1. Water is brought in equilibrium with a reservoir at 320 Kelvin directly. Process 2. Water is first brought in equilibrium with a reservoir at 310 Kelvin, then with the reservoir at 320 Kelvin. Process 3. Water is first brought in equilibrium with a reservoir at 350 Kelvin, and then with a reservoir at 320 Kelvin. The corresponding changes in the entropy of the universe of these processes are. So change in entropy for the universe. So we have to calculate entropy change for both water and reservoir. So for the first case, let us consider entropy change for water. Now it is simply m into specific heat of water ln of Tf by Tr. This is for water. So this will be m into Cw into ln of final temperature is 320 upon initial temperature is 300. So this is equal to delta Sw is equal to 0.06454 m into specific heat of water. So this is for water, and it will be same for process 1, 2 and 3. So we will not calculate it again and again. Next is process 1. So for process 1, reservoir is at temperature 320 Kelvin. So S for reservoir, it will be minus of m Cw into, this will be dq by T, and dq is m Cw into delta T upon its temperature. So this will be delta Sr will be equal to minus of m Cw, this will be same, and here we will have 320 minus 300, so that is 20 upon 300. So this is equal to minus of 0.0625 m into Cw. Now total energy, that is delta S1, this is equal to delta Sw plus delta Sr, so that is this 0.06454 minus 0.0625, so that is equal to 0.00204 m into Cw. This is for first process. Let's calculate for second process now. So for process 2, this delta Sr is equal to minus m Cw. It is first taken to 310 and then 320. So this will be, first change is 10 and then corresponding temperature is 310. Minus of m Cw, next it is 310 to 320. So again 10 upon 320. So this is equal to delta Sr is equal to minus m Cw 10 by 300 plus 10 by 320, and this is equal to 0.06351. So delta S2 is equal to again we have this Sw and minus this, so that is 0.00103 m into Cw. Next we have process 3. Now for process 3, delta Sr is equal to minus Cw. Then first it is taken to 350. So that will be 50 upon 350. Then it is taken from 350 to 320. So this is minus Cw. and 350 minus this, so this will be minus of 30 because difference is minus of 30, and then upon 320. So effectively it will be added. So delta SR is equal to MCW minus 50 by 350 plus 30 by 320, and that is minus 0.04911 m into CW. So delta S3 is equal to again SW plus delta SR, which is equal to 0.01543 m into CW. So now compare this delta S1, delta S2 and delta S3. From these values we can see delta S3 is greater than delta S1 is greater than delta S2. So here option B is correct. Here for water we have used this formula MC ln of Tf minus Ti, and for reservoir we have used this formula delta S reservoir is equal to dq by T, which is MCW delta T by T. Next question. A piston of mass m is fitted to an airtight horizontal cylindrical jar. The cylinder and piston have identical unit area of cross section. The gas inside the jar has volume V and is held at pressure P is equal to P atmosphere. The piston is pushed inside the jar very slowly over a small distance. On releasing, the piston performs an undamped simple harmonic motion of low frequency. Assuming that the gas is ideal and no heat is exchanged with the atmosphere, the frequency of the small oscillations is proportional. Now for this gas, we have PV raised to gamma is equal to some constant. So let us differentiate this. Then we will have P into differentiation of this gamma into V raised to gamma minus 1 dV plus V raised to gamma into dP. This is equal to 0. So from here we will get dP by dV is equal to this on the right hand side, so minus sign. Then we have gamma here. Then P V raised to gamma minus 1 upon V raised to gamma, which is equal to gamma P by V. So dP by dV is minus gamma P by V. Now we have force is equal to A into dP, area into change in pressure. So that is equal to, here dP we have calculated, so this will be minus gamma into PA by V into dV. So F is equal to, now dV is change in volume, which is equal to area of cross section into displacement. So this will be minus gamma PA by V, and this is equal to A into dx. This is change in volume. So this will be F is equal to minus gamma P, then we have A square upon V into dx. Now acceleration is equal to F by m. So this can be written as minus gamma PA square upon mv into dx, and this is equal to minus omega square into x. So omega square is equal to gamma P A square by mv. So from here omega is equal to A into under root gamma P by mv, and here it is given that it is unit cross section area, so A is equal to 1. So this omega is proportional to under root gamma P by mv. So here option B is correct. Question 47. A paramagnetic salt of mass m is held at temperature capital T in a magnetic field H. If S is the entropy of the salt and m is its magnetization, then we have dg is equal to minus S dt minus mdh, where g is the Gibbs free energy. If the magnetic field is changed adiabatically by delta H, which is tending to 0, and the corresponding infinitesimal changes in entropy and temperature are delta S and delta T, then which of the following statements are correct? Here it is given that changes are adiabatic. Now for adiabatic process, delta S is equal to 0. So delta S is 0 because delta Q is 0. So option B is correct. Next we have to change for delta T. So this is equal to this. So from this equation we can write S is equal to, this will be minus sign dou G by dou T, and that is at constant H. Also M is equal to minus of dou G by dou H at constant T. Now since G is a perfect differential, I can write dou by dou T of dou G by dou H. This will be equal to dou by dou H of dou G by dou T. I can change these variables like this. Now we have dou G by dou H is equal to M. So this will be dou M by dou T is equal to, this is dou G by dou T is S. So this will be dou S by dou H, and minus sign will cancel out on both sides. So this one we are getting. Now let us consider this. Let us consider dou T by dou H at constant S. This can be written as by chain rule dou T by dou S into dou S by dou H. We can write it like this. This will be at constant H and this will be at constant T. But we have this dou H by dou S. From here we have dou H by dou S is equal to dou M by dou T. So from here I can write dou T by dou S at constant H, and dou S by dou H is equal to dou M by dou T at constant H. So from here let us calculate this. So from here we can write dou T by dou H, left hand side as it is, and on the right hand side we have dou M by dou T at constant H upon, we have this can be, we can consider reciprocal of this. This will be dou S by dou T at constant H. So we are getting this. So this dt, it can be written as delta T, and this dH, it can be written as delta H. And as we know, these are opposite to each other. So here, from here we can write delta T is equal to minus of dou M by dou T by H upon dou S by dou T at H into delta H. So option C is correct. So option B and C are correct. Next question. For 1 mole of nitrogen gas, the ratio delta S1 and delta S2 of entropy change of the gas in process 1 and 2 mentioned below is. The gas is held at 1 atm and is cooled from 300 Kelvin to 77 Kelvin. Option B, second process is the gas is liquefied at 77 Kelvin. So consider first one, delta S1 is equal to, temperature is changing from 300 to 77. So it is going from Ti to Tf, and this is dq by T. So that is mCp, because pressure is constant, into integration from d2 to T. So this is equal to mCp ln of T final to initial. So ln of Tf by Ti. So this will be mCp into, we have ln of, it is going from 300 to 300 to 77. So 77 upon 300. And here value of Cp is given, and Cp is 7 calorie per mole per Kelvin. So into 7. So this is equal to m into ln of 77 by 300 into 7. So this is equal to minus of 9.5198. This is delta S1. Then delta S2 is, the gas is liquefied at 77. So this will be equal to minus of dq by T, which is minus of ml by T, which is minus of m. L is 1293.6 calorie per mole upon temperature is 77. So this is minus of 16.8 into m. So delta S1 upon delta S2 is equal to ratio of these two, which is 0.566 and which is roughly equal to 0.6. So rounding off to one decimal place, it is 0.6, and answer given in the answer key is 0.5 to 0.7. So these were all the questions from GATE 2022 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.